Good morning, everybody. I am Dr. S.S. Naidu, Assistant Professor in Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss about a very important topic in probability and statistics. It is probability mass function. Actually, in random variables, we have discussed about two main random variables. They are discrete random variables and continuous random variables. For discrete random variables, we define a probability function because it gives a certain numerical value. Such type of mass probability function, which is defined for discrete probability random variable, is known as probability mass function. So for discrete variable, we define probability mass function, and for continuous random variable, we define probability density function. Today we are going to discuss about probability mass function for discrete random variable. Probability mass function gives the probability that a discrete random variable will be exactly equal to a specific value. Here, that specific value is nothing but some numerical value. So, actually discrete random variable, it automatically itself gives a numerical value, a specific value. So, the probability mass function, which is defined on a discrete random variable, exactly gives a specific value. The probability mass function is only used for discrete random variables. So the probability mass function is used for discrete random variables. Whereas for continuous random variables, we define probability density function. Now, let us discuss this probability random mass function. For continuous random variables, the probability density function is used, which is analogous to the probability mass function. The probability mass function is also known as a frequency function. Why it is known as a frequency function? Because if x takes random variables, some x1, x2, x3, etc., x4, then depending upon the relative corresponding numerical values for x1, x2, x3, etc., xn. That's why it depends upon frequency. That's why it is also known as a frequency function. It can be represented numerically as a table in graphical form or analytically as a formula. In all these forms, we can define a probability mass function. Now, we will take an in-depth look at the probability mass function, its definition, formulae, and various associated examples. And in that, we can variate the difference between the probability mass function and probability density function also. Now let us define probability mass function. Probability mass function, PMF, probability mass function, and cumulative distribution function. See, what is the difference between probability mass function and cumulative distribution function? For probability mass function, from the variables from where to where, for them, they will give a specific numerical values. As a function, it goes on. Whereas for a cumulative distribution function, its a lower bound will be there, upper bound will be there. In between, it will be cumulative either in ascending way or in descending way. That's why it is called cumulative distribution function. Cumulative distribution function. That is the difference between probability mass function and cumulative distribution function. So these two are functions that are needed to describe the distribution of a discrete random variable. The cumulative distribution function can be defined as a function that gives the probabilities of a random variable being lesser than or equal to a specific value, numerical value. The CDF, cumulative distribution function of a discrete random variable up to a particular value, some x, it can be obtained from the probability mass function by summing up the probabilities associated with the variable up to x. Now, this probability mass function we can define by summarizing all this. The probability mass function can be defined like this. Probability mass function can be defined as the probability that a discrete random variable will be exactly equal to some particular value, some specific value. In other words, the probability mass function assigns a particular probability to every possible value of a discrete random variable. For that, so many examples we can see: flipping a coin, rolling dice, and all these things. The ultimate results will be some specific numerical values. Now let us see one example. Suppose a fair coin means it is unbiased. It is tossed twice. 2 times it has been tossed. Then 4 outcomes will come. They may be head and head, head and tail, tail and head, both tails. So the sample space S is equal to set HH, HT, TH, TT. Where head stands for H stands for head and T stands for tail. The probability of getting heads needs to be determined now. Here 4 are there. Among those 4, we can ask so many questions. What is the probability to get both chances are heads? Here, among those 4, 1 chance is there, head and head. Total 4 chances are there. So probability of HH is number of possible chances is 1 divided by number of possible chance is 1 by total number of chances 4. It is 1 by 4. Like that, number of questions we can frame on this. Let x be the random variable that shows how many heads are obtained. X can take on the values. Suppose in this example, a head can come in 0 ways, 1 ways, 2 ways. 0 ways means both tails will come. 1 way means head to, in 2 ways means head to tail, tail to head. So the probability that x will be equal to 1 is clearly 0.5. Thus, it can be said that the probability mass function of x evaluated at 1 will be 0.5. Now, probability mass function formula, let us see. The probability mass function provides all possible values of a discrete random variable as well as the probabilities associated with it. Means here only we can see the suppose if we flip a coin once, then probability to get head is 1 by 2, 50% chance. Probability to get tail is also 1 by 2, 50% chance is there. Sum of the probabilities 1 by 2 plus 1 by 2, 1. So let x be the discrete random variable. Then the formula for the probability mass function f of x evaluated at x is given as f of x is equal to p of x is equal to some x. Here capital X stands for random variable. Small x stands for a quantity. It is some specific value. It is specific quantity, specific value. The cumulative distribution function of a discrete random variable is given by the formula f of x is equal to p of x less than or equal to x. Previously I told about this. It has some limit, upper limit or lower limit. Here less than or equal to or greater than or equal to. If it comes like that, it is a cumulative distribution function. Perfectly it is some x is equal to x, then it is probability mass function. That is the difference between probability mass function, this, and a cumulative distribution function, this. So probability mass function of binomial distribution, let us discuss now. Binomial distribution is a discrete distribution that models the number of successes in Bernoulli trials. What are Bernoulli trials? How many attempts that we are doing there? How many random experiments we are doing there? All those are all called Bernoulli trials. They are called Bernoulli trials. Now, let us see what is the main difference between a probability mass function. It is defined for a discrete random variable, and probability density function. It is defined for continuous random variable. In probability mass function, that solution ranges between numbers of discrete random variables. That's why a specific number, a numerical value will come there. Whereas in PDF, the solution is in a range of continuous random variable because that value lies in some interval, some continuous interval. That's why previously earlier we discussed it there also. The measurements for height, weight, time, all these come under some range, some interval. That's why they come under continuous random variables. For them, we define that probability density function. Now, one more difference. The probability mass function uses only discrete random variables, whereas in probability density function, it uses continuous random variables. So, here the main items what we are discussing here is probability mass function, probability density function, probability distribution formula, the cumulative distribution function, less than or equal to, greater than or equal to are there. They come under cumulative distribution function. Next, binomial probability functions and their formulas also let us discuss now. Now let us see some applications of probability mass functions. These probability mass function plays an important role in statistics. It defines the probabilities for the given discrete random variable. This probability mass function, it integrates the variable for the given random number which is equal to the probability for the random variable. Means, it integrates means it sums up all whatever events are included in that. Their all values will be added and will be given a single numerical value. And this probability mass function is used to calculate the mean and mean mu and variance sigma square of the discrete distribution. Here mu, mean, sigma square, variance, sigma, standard deviation. So standard deviation is equal to, that's why standard deviation is equal to plus or minus square root of variance. So this probability density function is used in binomial and Poisson distribution. Both binomial and Poisson distribution come under discrete distribution, discrete probable random variables. So this binomial and Poisson distribution to find the probability value where it uses discrete values. Discrete values means specific numerical values, definite values they will give. Some of the probability mass function examples that use binomial and Poisson distribution we can discuss like that also. See, probability mass function of a binomial distribution. Let us see. In the case of the binomial distribution, the probability mass function has certain applications, such as to find the number of successful sales calls. See, suppose a car sales company is there. On that particular day, how many orders they have been received? Among them, how many orders were confirmed? How many orders were delivered on the day? All this particular data we can categorize to make a probability mass function. Like that, to find the number of defective products in the production run, means in a factory some bulbs are being made. Suppose randomly it had been taken that for every 100 bulbs, some 2 bulbs are found to be defective. Then we can establish a probability mass function for that given data. Next, finding the number of heads, tails in coin flipping. Suppose that coin flipping may be once, twice, thrice, or 2 coins may be flipped at a time, or more than the 3 coins, 4 coins also flipped at a time. These are all random experiments. At that time also, we can establish a probability mass function for all these trials. And calculating the number of male and female employees in a company. Suppose if that company is maintaining a specific ratio for male and female employees, then definitely we can establish a probability mass function for that company. Finding the vote counts for 2 different candidates in an election. Suppose randomly we are observing the vote counts for the two candidates. Then after a particular round, we can establish how the trend is going on, the winning trend is going on between those two candidates by establishing a probability mass function. Like that, we can establish a probability mass function for different situations. Consider an example that an exam contains 10 multiple choice questions with 4 possible choices for each question, in which the only one is the correct answer. To find the probability of getting correct and incorrect answers, the probability mass function is used. How? PMF is equal to 1 by 4 for correct answer, 3 by 4 for wrong answer. See why among those 4 only one is the correct one. That's why its probability is 1 by, for correct one probability is 1 by 4. For incorrect, the probability is 3 by 4. Like that. And this 1 by 4 and 3 by 4 are specific numerical values. Here we can establish a probability mass function as 1 by 4 if E is correct, 3 by 4 if E is wrong. This is a probability mass function. Like that we show probability mass function. Here clearly you can see a specific numerical value we are getting there, 1 by 4, 3 by 4. That is the main feature of probability mass function. Now let us discuss this probability mass function for Poisson distribution. Likewise, binomial probability mass function has its applications for Poisson distribution also. To find the monthly demands for a particular product. See, monthly demands for a particular product will go exponentially. That's why e to the power some x exponentially. That's why this example comes under Poisson distribution. What is the definition for Poisson distribution? P of x is equal to e to the power minus x into lambda power x divided by x factorial. So the monthly demands for a particular product obeys this formula. Like that, calculating the hourly number of customers arriving for a bank, it is also exponential. So this comes under Poisson distribution. Finding the hourly number of accesses to a particular web server, definitely it comes under exponential. So it is Poisson distribution. Finding the number of typos in a book, they will also will be increased in exponential order. So this also comes under Poisson distribution. Now let us see the notation and some other details about this probability mass function. For a discrete random variable, each possible value must have a non-zero likelihood. Non-zero likelihood, why we are telling here now only we saw 1 by 2, 3 by 4, 1 by 2, 1 by 2. Like that, if the probability is 0, already you know it is impossible event. That's why specifically it is written as a non-zero likelihood. For a discrete random variable, each possible value must have a non-zero likelihood. Additionally, the probabilities for all possible values must sum to 1. Means sum of all probabilities should be equal to 1. Because the total chance is 1. One of the values must occur for each opportunity. For example, the chance of rolling a particular number on a die is 1 by 6. The total probability for all 6 outcomes equals to 1 by 6, 1 by 6, 1 by 6, 1 by 6. For a single roll of a die, you inevitably obtain one of the possible values. Or when you flip a coin 5 times, you will always get 0 to 5 heads because each outcome has a non-zero chance and they sum to 1. So, if the probability mass function has a finite number of values, you can list all the outcomes and their likelihoods in a table, producing its probability distribution, which will show next. So, the standard notation for a probability mass function P of x is equal to x is equal to f of x. This is the standard notation for PMF, probability mass function. Here, capital X is the discrete random variable. Small x is one of the possible discrete values previously we discussed. F of x is a mathematical function that calculates the likelihood for the value of x. So, putting it all together, P of x is equal to x is equal to some f of x means the chance of variable x assuming the specific value of some x, it is equal to f of x. For example, when considering 3 heads in a series of coin tosses, the PMF notation is written as, suppose P of heads is equal to 3 is equal to f of x. This is the particular PMF notation for this example. But what function do we use to perform the calculation? That depends upon the discrete variable. How that discrete variable is there, depending upon that we calculate. Probability mass function, one more example, let us see. The coin flip scenario requires the binomial distribution because it calculates the probability of exactly x events occurring in n trials. X events, n trials. For example, it can find the likelihood of 3 heads occurring in 5 coin flips. Then, using binomial notation, we can define its mass, probability mass function f of x is equal to NCR formula. NC in place of R, x is there, into p to the power x. P means successes. P power x into 1 minus p means it is q term, failures. 1 minus p to the power n minus x. It is our standard binomial notation for general term. That we can write take it as probability mass function here. Here, N is equal to number of trials, X is equal to number of successes, X is equal to number of events that we are taking there. P means probability of success. Here NCX, number of combinations without repetition. So for this example, we are skipping some calculations. However, we can work out examples. Suppose this table, let us see this table. This table depicts the likelihood of obtaining each number of heads from 0 to 5 when you flip a coin 5 times. N is equal to 5. Here, number of heads and their probabilities they are discussing now. If the probability to get number of heads 0 is 0.03125, the probability to get one head is 0.15625, the probability to get two heads is 0.31250, the probability to get three heads is 0.31250, the probability to get four heads is 0.15625, the probability to get all the 5 heads is 0.03125. There are the sum of the all probabilities should be 1. Here it is becoming 1. Now, if you see this table carefully, we can draw a graph like this. Here notice how we obtain non-zero likelihoods for all outcomes and they sum to exactly 1. Here on x-axis we are showing heads from 0, 1, 2, 3, 4, 5. On y-axis we are showing their respective probabilities. Then this graph shows the number of heads in 5 coin tosses. Here in binomial, number of trials n is equal to 5. Probability for each for getting head and tail, it is 0.5. It is known to us. Then that graph is coming like this. Now let us discuss types of probability mass functions. Choosing the correct probability mass function depends on the nature of the discrete variable and what we need to model. Fortunately, various probability mass functions exist there. Binomial distribution for the number of successes within a set of trials, such as heads in a series of coin tosses. Poisson distribution for count data, such as the count of store patterns per day. Uniform distribution for events with equal probabilities, such as rolling a die. These are all various probability mass functions. Now, negative binomial distribution. What is negative binomial distribution? It is for the number of failures. It is for the negative binomial distribution is for the number of failures before a specified number of successes occur, such as the number of attempts before making 3 successful sales. Geometric distribution for the number of trials before a success occurs, such as the number of tosses before getting heads on a coin. Hypergeometric distribution for sampling without replacement. Hypergeometric distribution is used for sampling without replacement, such as the number of red balls drawn from a jar of mixed colored balls, where the proportion of red balls is known to us. Let us see a brief recapitulation. Probability mass function, it is defined for the discrete random variable. See, this probability mass function, and what is the main difference between the probability mass function and cumulative distribution function? Probability mass function, it is defined as P of some x is equal to x, whereas cumulative distribution function CDF is defined as some x less than or equal to x. This is CDF, cumulative distribution function. This is PMF, probability mass function. So, probability mass function, it is defined for a discrete random variable, and it will be exactly equal to some particular value. We can see while flipping a coin, while we roll a die, etc. So, we can define this mass function for different situations, which will, in all situations, it will give a specific value, a numerical value. Now let us one time see probability mass function of binomial distribution. It is for Bernoulli trials. And the main differences between probability mass function and probability distribution function can be categorized like this. Solution ranges between, while in probability mass function, solution ranges between number of discrete random variables, while in probability density function, the solution is in a range of continuous random variables. In probability mass function, it is used for discrete random variables. In probability density function, it is used for continuous random variables. So, we can see so many applications of this probability mass function, where with the help of them we can use it to calculate mean and variance of discrete distribution. So, probability mass function exemplifies binomial and Poisson distribution in so many ways. So, the PM of binomial distribution can be seen to find the number of successful sales calls, to find the number of defective products in the production run, in finding the number of head and tails in coin flipping, while we calculate the number of male and female employees in a company, finding the vote counts for two different candidates in an election. We can use probability mass function. In that same way, we define probability mass function for Poisson distribution, like to find the monthly demands for a particular product, for calculating the hourly number of customers arriving for a bank, for finding the hourly number of accesses to a particular web server, for finding the number of types in a book. So, in a probability mass function, the main notation is the value must have a non-zero likelihood. So probability mass function is written as P of x is equal to some f of x. So the probability mass function for a binomial distribution can be written as f of x is equal to ncx p to the power x into 1 minus p to the power n minus x. Here n represents for number of trials, x is for number of successes, p is for probability of successes, ncx is for number of combinations without repetition. For that, one example also we have discussed here. Some types of PMFs also earlier we have discussed. So we have discussed negative binomial distribution for the number of failures. Like that, geometric distribution for the number of tries before a success. In the same way, we discussed about hypergeometric distribution for sampling without replacement. So all these things we have discussed. So this probability mass function plays an important role to give a specific value for a discrete random variable. Thank you. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.